Hi, everyone. Welcome to my talk. I would like to thank the organizers for inviting me to give this talk. I want to talk about the pointwise while laws for shooting operators with singular potentials. This is a joint work with Xiaoqi Huang from Johns Hopkins University. Let me introduce some background about this problem. We studied shooting operators on a smooth, compact, n-dimensional Riemannian manifolds without boundary. So this is time-independent shooting operators equal to the Laplace-Dodge-Me operator plus a real-valued potential function in the calculus. So the calculus condition is given by the limits of this integral equal to 0. This integral is taken over a shrinking ball where radius goes to 0. And the wave function Wn here is almost a fundamental solution of the Laplacian. Here, dgxy is just a Riemannian distance on the manifold. So we can see that this calculus potentials must be integrable on a compact manifold. And any by Holder's inequality, any LP function with p greater than n/2, it is contained in the calculus. Here, n/2 is the critical exponent because if p equal to n/2, this kind of LP functions can be not in the calculus. So we introduce this calculus for the potentials to ensure that our shooting operators is self-adjoint and bounded from below. And this calculus condition is almost a minimal condition to ensure the shooting operators satisfy this property. And because our manifold is compact, under this calculus condition, the spectrum is discrete. And eigenfunctions are continuous. Because the operator is bounded from below, in this case, we may add some constants to the potential such that our HV is a positive operator. So we can write the spectrum of the square root of HV into an increasing sequence, tau k. Here we consider the eigenvalue problem of this operator, HV. And we also assume that our eigenfunctions associated with the eigenvalue tau k are L2 normalized, which means that it has L2 norm equal to 1 on the manifold. So a key tool to study the eigenvalues of the operators HV is the heat kernel estimate. For the smooth potentials, the heat kernel estimates were proved by Li and Yao, and it was generalized by Sturm to any potentials in the calculus. Indeed, we may slightly generalize the calculus condition. We just need to assume that the negative part of the potential is in the calculus, and only assume that the positive part is integrable. And we can still have the heat kernel estimate. Before introducing the problem, let us overview the previous results, the classical results on the while law. So the while law for the classical Laplacian tells us that we can estimate the number of eigenvalues less equal to lambda by the following formula. Here the leading term. The leading term is lambda to the n, where coefficients depend on n and the manifold. And the error term is lambda to the n minus 1. And this error term is sharp because you can consider the example on the standard sphere Sn. And this while law has been has a long history, and it was first studied by Weil in 1911, and later it was generalized to the manifold and also to the pseudo-divine operators by Leviton and Kumovic and Homander. We may to introduce the pointwise while law, we need to define a spectral function. So we consider the indicator function of this closed interval from minus lambda to lambda. And we denote this special function. We define the special function by the sum of all the square of the eigenfunctions with eigenvalues less equal to lambda. Here we consider two kinds of eigenfunctions. Here ej0 is the eigenfunctions for the h0, and e tau k x is the eigenfunctions for hv. And we denote the square roots of the h0 by p0, and denotes the square root of hv by pv. The classical sharp pointwise Weyl law is the following. So we can see that the special function has the following estimates. The leading term is lambda to the n with coefficients only depending on n, and the coefficients is independent of the manifold. And the error term is big O lambda to the n minus 1. And this estimate is independent of it's uniform in x. And it is sharp because you can verify the error term cannot be improved on the sphere. And because our eigenfunctions are L2 normalized, which means that L2 norm is 1. So if we can take integration on both sides to get the sharp Weyl law in the last page. So we can take integration. And this is the eigenvalues, the number of eigenvalues less equal to lambda. So the pointwise Weyl law is stronger than the sharp Weyl law in the last page. Recently, Huang and Sok, my collaborator Huang and Sok studied the pointwise Weyl law, studied the Weyl law for the Schrödinger operators with potentials in the Carnot class. They proved the following sharp Weyl law, which has the same form as the classical Weyl law. And later, it was generalized. It was considered more carefully in the three-dimensional case, and in there, by Frank and Sabin, they show that this condition can be relaxed to be the Carnot class plus Ln over 2. So for all the potentials that can be decomposed into a function in the Carnot class plus another function in the Ln over 2 space. And Frank and Sabin also consider here they only prove this for 3 dimensions, so it's 3 over 2. And it's natural to consider the pointwise Weyl law for the Schrödinger operators. Frank and Sabin proved some results in 3 dimensions, but the questions for higher dimension or dimension 2 are still open. So this is the question we want to study. So the first result we proved is the pointwise Weyl law with a little o lambda to the n error term. So we proved that for the potential in the Carnot class, we can estimate the special function. Here the leading term is the same as the classical pointwise Weyl law, but the error term is little o lambda to the n. And in this result is known to was known to Frank and Sabin, and they proved this result under the same condition. And they also show that this condition and this error term is sharp under this condition, because they are able to construct examples to show that this error term cannot be improved to 3 minus eta. Here n is equal to 3 for any eta greater than 0. We also expect our results will be sharp in any dimension, and we are still working on the sharpness of this result. And the second theorem we proved is that under a stronger condition, Ln, we can have a sharp error lambda to the n minus 1 for the pointwise Weyl law. The leading term is the same as the classical pointwise Weyl law. And for smooth potentials, this pointwise Weyl law, of course, is known in the history. It was proved by Commander for general pseudo differential operator. And when n equal to 3, Frank and Sabin proved the same pointwise Weyl law with sharp error term under a different condition. And this condition is satisfied by all the LQ function with Q greater than 3. So this condition is different from us, and both the conditions are satisfied for Q greater than 3 for functions in LQ and Q greater than 3. And in the paper of Frank and Sevin, they construct examples to show that the error term lambda to the n-1 can maybe not true if the function is in LQ for Q less than 3. So the classical pointwise Weil law, the sharp error term fails to hold for potentials in the LQ Q less than 3. And therefore, here in 3 dimension, Q equal to 3 is a threshold for the sharp pointwise Weil law. And in general, we expect that the condition Ln is sharp for any dimension n. And more specifically, the examples used in the Frank and Sevin is the following. So it's a distance function. Here we fix x0 and the distance function to x0 to the power eta minus 2. Here eta is a number less than 1 and greater than 0. And multiplied by a smooth cut of functions, which is equal to 1 near the 0. And they are able to show that in 3 dimension, the error term is almost lambda to the 3 minus eta near x0. So if eta is very close to 0, this error term will be large and very close to lambda to the n. And this shows so this example can be used to show the sharpness of the results. And we are still working on the general dimensional case, because this result is only known in 3 dimensions but unknown for other dimensions. We are still working on the sharpness in other dimensions of our 2 theorems. And clearly, this potential is in the K2 class, and it is an LQ for all Q less than n over 2 minus eta. So if eta is close to 0, and this Q will be less than m. This Q will be very close to n over 2. If eta is very close to 1, this Q will be very close to 1 plus, very close to n. So we expect that the error term will be lambda to the n minus eta at 0. And it can be used to prove the error term and the conditions are sharp in our 2 theorems. Now we can introduce the main approach in our paper. So the first step is to represent the spectral function using Fourier transform. We use the Fourier transform of the integrated function, which is equal to 2 times sine lambda t over t. So we can rewrite the spectral function using the wave kernel cosine TPV. And the spectral and this is the spectral expansion for the wave kernel. Recall that we have this classical pointwise Weil law. So we just need to estimate the difference of these 2 spectral functions. If we can show that the difference between these 2 spectral functions satisfy the desired error estimate, the error bounds, uniform in X, then we are able to prove the theorem. That is, if V is in the K2 class, we want to prove the difference uniformly in X is little o lambda to the n. And if the potentials is in Ln, we want to show the difference is big O lambda to the n minus 1. Okay. To study the difference of these special functions, we need to use the Duhamel's principle to consider the difference of the wave kernel for the cosine TPV and cosine P0. Here, PV is the square root of HV and P0 is the square root of H0. So we may use a spectral theorem to rewrite this wave kernel in the difference of the wave kernel in this form. Okay. So we just need to estimate this difference of the spectral functions and prove that they satisfy the desired error bar. And the idea to estimate this difference is to decompose the sum with respect to the frequency. There are two kinds of frequencies, lambda j and tau k. We decompose the frequencies into low frequencies and middle frequencies and high frequencies. Here we mean low frequencies means the frequency less equal to less than lambda over 2, and middle frequencies means that the frequencies between lambda over 2 and 10 times lambda. And high frequencies means the frequencies larger than 10 times lambda. And then we can decompose the sum into several pieces, and we can estimate this using some tools from zero differential operator and the other harmonic analysis tools. So the tools to estimate the pieces comes from the decompositions, contains the kernel estimates of the pseudo differential operators. So this lemma can be found in in Zock's books and also in the harmonic analysis books by Sang. So if M is a function, a smooth function, satisfy this condition, then MP0 here P0 is the square root of the Laplacian plus 1. Then MP0 is a zero differential operator of order mu. And this kernel satisfies the condition. So if mu is equal to -2, you can say that this one will be equal to 2 minus n, and it is similar to the wave function in the K2 class. So this is the kernel estimates for our pseudo differential operators. We will use frequently in the proof. And the second result we used is the classical spectral projection bound by Zock. It is L2 to LP estimates for the spectral projection operator with length equal to 1. And this result is sharp on any manifold. And these results can be generalized to the potentials in the intersection of the K2 class and the space Ln over 2. And in particular, Blair, Sear, and Zock proved the following spectral function bounds for HV. These results tell us that the L2 to L infinity bounds for the spectral function. So it has a bounds equal to lambda to the n minus 1. It's related to the L2 to L infinity bounds for the spectral projection. And in particular, this condition Ln over 2 is not necessary if n is equal to 2 or 3. And the hit kernel bounds by Li and Yao and Sun are also important in our proof. It can have a useful corollary, which is useful rough eigenfunction bounds for the potentials in the K2 class. And to estimate the pieces coming from the decomposition, we need to deal with the mixture of different frequencies. So we have to introduce a lemma which can be used to separate different frequencies. That is the lemma 8 here. So for the potentials in Ln, we can prove this useful lemma by using Holder's inequality and the fundamental theorem of calculus. And it can be used to separate different frequencies. Okay. And here are some remarks about our problem and the theorems. So our results extend the three-dimensional results by the Frank and Sabin to any dimensions. And their proof use classical methods by Kumovic and relies on the Tauberian estimates and the parametrics the parametric estimate for the resolvent. But it's not clear to us how to adapt their approach to deal with general manifold. And it seems possible to prove the sharp pointwise Weyl law under some conditions different from Ln, similar to the conditions in Frank and Sabin. We may replace this Ln condition by general conditions like dxy, dx here is m minus 1. When n equal to 3, this is 2 power 2. So it has been considered by Frank and Sabin in their paper, 3-dimensional paper. So it seems possible to prove some results in any dimension under this condition. It's less equal to infinity, so y in m, with distance less than some epsilon prime. And it seems possible to improve this sharp pointwise Weyl law for the Schrödinger operators under some geometric conditions on the manifold. And there are also some interesting open problems concerning this topic. For example, when we consider similar problems on the compact manifolds with boundary, consider the same problems for the magnetic Schrödinger operators. Here, the magnetic, the potential of the magnetic field can be in L2. It has been discussed. This is a rough potential, a rough or magnetic potential, and has been considered by Barry Simon in the survey paper by Barry Simon. Okay. Okay, thank you for listening.